All right, in the last couple of days, we talked about projectile motion, and we kind of culminated with a very elegant problem, which I call classic problem number 2. And can someone tell me what makes something a classic problem number 2? Go ahead, anyone. Oh, not in the chat, man. Out loud.
It's a full parabola.
Right. The path of the projectile, the trajectory, is a full upside down parabola launched from the ground, going up and landing on the ground. And we found things such as the distance, the range, we found the time, and today we're actually going to get a look at this maximum height right here. But a classic number 2 problem is launched from the ground, landing on the ground. It's the most elegant of all the projectile motion problems. And today, I would like to solve this problem without any numbers, just with symbols, and see if we can come up with some equations that will be generically true, always true for this type of problem. So let's go ahead and make the list of knowns and unknowns. The starting position in x can always be chosen to be 0, as can the starting position in y. The final position in the x direction is usually unknown to us. They call it the range. And the final position in the y direction is 0 because this thing lands back on the ground. Now, this is where we get a little difficult. The starting velocity in the x direction is the starting velocity overall times the cosine of the angle. So we're given a starting velocity and an angle on the original problem, and we would componentize it in this way to find the starting velocity in the x direction. The starting velocity in the y direction is similarly vi times the sine of theta. The final velocity in the x direction is equal to the initial velocity in the x direction, and that's because the acceleration in the x direction is 0, so this velocity never changes. However, the final velocity in the y direction actually reverses, and by the time it lands, it will have the same speed, but the opposite direction of y direction velocity. I have not proven this to you yet, but we can do that at any time, anybody who's curious. And the acceleration in the y direction is negative g. Negative because it's apparent that I've chosen upwards to be my positive direction, and g because if I'm not going to use numbers for any of this stuff, I don't need to use a number for that. Ooh, the time, we don't know. So let's go through and solve this problem in the way we did, what, yesterday or the day before, only with just symbols, no numbers. So the very first thing we did is we solved the y Swiss Army equation, and from that we got the time. So here's the y Swiss Army equation. And we'll put in the symbols 0 and 0 plus vi sine theta times t minus g over 2 times t squared. By putting a minus g in for the acceleration in the y direction, we flip this to a minus sign and we're over 2. Now the trick that we pulled last time is we divided through by t, which we can still do. This is still classic number 2. And so we wind up with 0 equals vi sine theta minus g over 2 times t. And when you solve that by bringing this over to the other side and then dividing or multiplying by 2 over g, you wind up with t equals 2 vi sine theta over g. And this formula is always true. This is the time of flight. So if you knew that you had a classic number 2 problem, you could just jump to this equation and put these things in there, vi, sine of theta, and g, and you would know how long this thing was in the air. Isn't that cool? What's the next thing that we did? Well, we did the Swiss Army equation in x to find the range. xf, which is going to be the maximum distance, is going to be 0 plus vi cosine theta times t, but we have t up here is 2 vi sine theta over g, and this last term is going to be 0 because ax is 0. It kills the entire last term. So it looks like the range of this projectile is going to be 2 vi squared cos theta sine theta over g, which is a perfectly valid equation, but it's not quite as elegant as it could be. Math teachers will tell you that there's a trig identity that has cosine times sine theta being equal to 1/2 of sine squared, or no, sine 2 theta, not sine squared, excuse me. Cosine times sine is equal to 1/2 of sine of 2 theta. So let's make that substitution, and we'll wind up with vi squared sine of 2 theta over g, and that's equal to r, and this is the range of the projectile. This is how far it will go. You could even use this equation backwards. Put the r you want the projectile to land at, and then you can figure out what combination of vi and 2 theta. You can even take a derivative of this and figure out that the maximum range occurs. Take a derivative of this with respect to theta, and you can figure out that the maximum range occurs at a theta of 45 degrees. You could even show, using this equation, that angles that are a certain number of degrees above 45 and angles that are the same number of degrees below 45 result in the same range. All of that comes out of this, doing it with no numbers and letting the cancellation take care of business. All right, are there any questions about this right now? Keep in mind, this only works if we have a classic number 2 problem where these things are true. Now I'm going to take a little deviation because we said we were going to talk about this maximum height. And in order to find the maximum height, we are clearly not going to let the projectile come all the way back down to the ground. We are going to stop this problem in the middle. So we're going to change some of these initial assumptions. The time will not be this much. It will actually be half of this much. But some other things are going to change in here. So if we make those changes, we can find the maximum height of the projectile. So the changes that we need to make look a little something like this. Xi will still be 0. Yi will still be 0. Xf will be, I don't know. Yf we're going to call the height, but we don't know what it is. Vix is still Vi cos theta, as is Vfx. I'm going to put the ditto marks there. Viy is Vi sine theta, but Vfy equals 0. When we're solving for the maximum height, that happens when the vertical velocity is momentarily 0. Remember, it starts as a positive number. It's going to go to a negative number when it hits the ground. But the maximum height is reached when you stop going upwards and you have not yet started coming downwards. You have 0 velocity. Acceleration in the x direction is 0. Acceleration in the y direction is minus g. And the time, again, we don't know, but I'm telling you it's half of that other time. So if we were to solve this for the using the no time equation, we would be able to get the maximum height. So yf minus yi is h minus 0, or h. 0 squared is 0, and this is what the initial velocity is squared. Moving this to the other side and doing some dividing, we find out that the h, the maximum height, is vi squared sine squared theta over 2g. This is the maximum height formula. So as long as you knew you were dealing with a classic number 2 problem, these 3 formulas that I have derived, the time of flight, the range, and the maximum height will all be true, and you can get them off of your simple starting conditions of VI and the angle theta and the strength of the gravity on the planet you're working on, G, which is, most of us are going to be on the Earth all of our lives, therefore that G is pretty predictable. There is one more thing we can do without any numbers, and it's a bit of a bear, but it can be done. What can we solve for an equation for the path that doesn't involve time, where y is equal to some function of x? Can we do that? We can, as long as we treat xf as some arbitrary x that we don't know what it is, and yf as some arbitrary y that we don't know what it is, and we get rid of time somehow. So we can write down the y Swiss Army equation. Y is going to be 0 plus vi sine theta times t minus g over 2 t squared, and x equals 0 plus vi cos theta times t plus another 0 for the acceleration term that goes away. And we could solve this one for t and plug that t in over here and get rid of t. T is what they call in the world of mathematics a parameter. I find that parameterized equations are easier to handle. You vary the parameter and you find out what your x and your y are. But in math class, they often want to know, how does x vary with y or y with x? And you need to get rid of your parameter. The parameter in this case actually has a meaning. It is the passage of time. But let's just do this. To solve this for time, t equals x over vi cos theta. And we're going to substitute that in. So y is going to equal vi sine theta times t, which is x over vi cos theta, and then minus g over 2 times this thing squared, x squared vi squared cosine squared theta. Okay, this term cancels really nicely. The vi's cancel, x stays there, and sine over cosine is tangent. So the first term is just x tan theta. The second term is going to have a gx squared on the top and a 2 vi squared cosine squared theta on the bottom. And this is the actual shape of the trajectory. This is a function for y as a function of x. And you can see it's a parabola. You can see it's an upside down parabola. And it's got this extra x term, which shapes the parabola in a way. I don't know if you guys have ever played with what the different terms in a quadratic equation do to shape the parabola. It's kind of fun to do that sometime. You might want to do that. I actually had this video game called Island of Dr. Brain, and it was one of the puzzles was to vary some parameters so that you could shape a parabola and open a door. It was kind of a cool game. So I have a little bit of a headache because I'm not a theoretical physicist. This is what theoretical physicists do all day. They put formulas together, no numbers, no nothing, and they come up with relationships, and then we experimentalists go out and measure the things we need to measure in order to test the theory and see if it's right. And a lot of physicists love just doing this kind of stuff, and that's not me. But this is what you can do if you don't have any numbers. And I must warn you again that this only works if you have a classic number 2 problem. You must have this shape, you must have these setups, and then it will work. If anything else is going on, these equations are not valid. Okay? And how do you handle the situation if you don't have a classic number 2? Then you have to go through the procedure with the numbers you have. But if you have a classic number 2, I've just gone through the procedures and come up with the results. Some people like this, and those people are called engineers.